Dr. Arnab Bose currently is working as an assistant professor in the Department of Electrical Engineering at National Institute of Technology, Rourkela, and associated with Center of Excellence on Renewable Energy Systems. He has been actively involved in research on different control and power electronic converter design for renewable power generations. He is an IEEE senior member and chartered engineer. Currently, he is associated with four esteemed projects such as Bilateral International Research Project of Indo-United Kingdom Joint Project, that is UKIERI 2019 at NIT Rourkela, collaborated with Northumbria University, Newcastle, United Kingdom. Second one is Indo-Sri Lanka Joint Research Program at NIT Rourkela, collaborated with University of Moratuwa, Sri Lanka. Third one is Impacting Research, Innovation and Technology 2019, Imprint second chapter at NIT Rourkela, etc. Recently, he has received Young Scientist and Technologist Award from DST Government of India. He is author of more than 50 research publications in international journals and conferences of repute. His work has been accepted by IEEE Transaction on Industrial Electronics, IEEE Journal of Emerging and Selected Topics in Power Electronics, International Transaction on Electrical Energy Systems, IET Power Electronics, etc. His research interest includes the design of charging station of EVs, control of microgrid or smart grid, switch mode power converters, nonlinear dynamics of switching converters, machine drives, etc. Dr. Ghosh is also supervising UG, PG and PhD students in the domain of design of power electronic converters and controls for smart grid and hybrid microgrid. So now I would request Dr. Arnab Ghosh sir to begin the session. Thank you.
Thank you, Ananya, for introducing me. So just now I am sharing my slides. I hope my slide is visible from your end.
Yes, sir.
Okay. And very good morning and warm welcome to all my esteemed participants on the day two of our NAMPED course. Okay, so today I am going to deliver some brief idea and some it's quite informative sessions. Okay, so on the design of switching converters and power management for the microgrid application. Okay, so that sessions right now I'm working some DST seed divisions, DST seed division project that seed means Science for Equity, Empowerment and Development divisions. Okay, so the topic is solely concerned about our some of the part of our project work, and it's not like only totally theoretical, totally basically it's not total experimental part. Okay, some of the information, some of the theoretical part, some of the simulations part. So I am trying to accommodate some several aspects of our microgrids. Okay, especially we are working in the nanogrids. Okay, so that motivations of that lecture, or the motivations of the session to give some basic idea on the microgrids. And I hope yesterday a lot of sessions was already conducted, and from that session we can understand what are the basic idea of the microgrid. Still, I hope some of the points as a power electronics, from the dimensions of the directions of the power electronics converter aspects, we should focus some of the portions of the microgrid, as well as what are the basic ideas of the microgrid. I'm keeping these informal sessions, informative sessions for all the participants as well as our students. Okay, so when we're working on that on that area. So first we need to know about what is the motivations for working in this domain. Okay, first we need to know about what is the motivations, why it is important, and how we are going to implement it. Okay, so first thing is that what is the importance of these kinds of work. Okay, why we are going to discuss about switching converters. Okay, so switching converters, you know, the title contains of separate terms are there that you know that says switching converters. Okay, so what is the meaning of that money? What is the importance of the converters? That we need to know first thing. Okay, so you know that currently that all the you know that there is a lot of limitations for the conventional generations process. Like we conventionals means normally we are more focused on that fossil fuels for our electricals, for our power generations. Okay, so now government are trying to change the mindset of our common person to switch to the renewable sources and renewable sources instead of the conventional sources. Okay, still it is the demand, as the demand is very high of our load end, and from the generations of the renewables is not so much. If we trying for the best, so it is, then we can recover some of the portion, but still it is there is a huge gap as per the generations and the band and the demand. Okay, so we have to reduce the band gap. That's why that's the basic motivation to working on this field. And why the power converters or power electronics converters are important. Basically, when we're working in that microgrid domains or microgrid applications or the nanogrid applications, so we are using several types of renewables. Okay, means renewables sources of energy. So we have to integrate the renewables to our microgrid. So what will be the interfacing medium? That power electronics converters are normally interfacing medium for that cases. Okay, so that's the basic issues for using the different types or different topologies of the power electronics converter. In this work we are discussing about very basic some basic power electronics converters modeling, and some of the results. Okay, how they are related to that work, that some of the portions will going to I'm going to discuss here. Okay, still a lot of converters are also be there that will not be discussed here, but that can be work fine. Okay, so here we can also see another aspects of that presentation, that is the power management of the microgrid application. So why that power managements are needed? Okay, so another thing is that the renewables, whatever we are using there, the main problem of the renewables is that intermittency. Okay, means you know that changes of that if we are considering that solar photovoltaic. Okay, so changes of the solar irradiations and daytime, night time. Okay, so all the time it will not work in proper manner, as well as if we're considering the wind. Okay, so same problem also happens. Some of the time you can see that there is a high speed of the winds, and sometimes you can also see there is a not presence of the so much speed of the wind. So the intermittency natures, and it's not like that only daytime, it's also the season time. Okay, but you can see that if if we getting the real-time data. Okay, if we collecting the real-time data, so you can also see their nature is not the steady. Okay, so it is fluctuating. Okay, that's why we are talking about the intermittency. So that's why the power management concept also be there. Okay, so power management means there are a lot of algorithms also be there in the literature, but in this work we are thinking the same thing from a different point of view. Okay, that points also coming some of our some of our work that will be discussed also here in the later portions. Okay, so that is another motivations for discussing the topic here. Okay, so now we can understand what is the importance of thing, the importance of that to interfacing the renewables to our microgrid. Okay, to reduce the uses of that conventional fuels. Okay, so you know that from where we are belong, that's if you see the surrounding areas, okay, that we know that there are a lot of villages are there, okay, so and okay, if we are giving them the self-sufficient generation from their own end, some of the portions also happen. It's quite some of the places are too remote, okay, and electricity, some portions are not there, okay, so that's why if we able to provide them to such type of setup, okay, nominal setup for that one generations for the rural electrification scheme, so they can also utilize that their own generations as well as they can also utilize they can also develop their own generating also utilize their generated power for their daily applications. Okay, so that's the way and motivations of that point of view. And now we are going to discuss how it is working. That's why we'll start from there. So first thing is that you know that say there is some issues, like you know that due to the fossil fuel generations there is a huge global warming. Okay, so that's why there's an Paris Agreement happened. Okay, a few couple of years back. Okay, so not couple of years, more than I think so. Okay, so the government of India is taking an oath that within 2030 they are trying to reduce 2 degree centigrade from the total temperature emitted from due to the industrialization. So for getting these kinds of satisfied outcome, so we have to follow some of the aspects. Okay, what are the points? So conservations of the renewables, conservations of the forest, like that. If we go for that, if if we are trying to reduce the global warming, so definitely we have to natural resources should be we should keep more conservations on that. Okay, so another thing is that you know that different sectors, okay, sector elevated climate change. So first one is that water, forest, okay, we can also conserve there. Then the more important thing is that the utilizations. Okay, utilization aspects. Utilization means whatever generation you have, now how optimally and how efficiently, in the point of view energy efficiently, we are utilizing that power. Okay, suppose now you know there is a, you know, in the case of lighting, initially there is a tungsten filament lamp, now it is switched to fluorescent lamp, after that CFL, now we are using also LED. Okay, so if you change their rating, okay, so it was in I'm talking about only illumination load. So a tungsten filament lamp, it is normally early days, if you see there is a 5 or 10 watt was there, but their luminous intensity was not so much good. Okay, so for getting better some normal conditions of lighting, you have to get at least 100 watt bulb, okay, or filament, tungsten filament bulb. Now if you go for the CFL, that directly reduce from 100 watt to 40 watt. Okay, then if we going for the fluorescent lamp and CFL is quite less than your fluorescent lamp. The rating, okay, means what is rating, now we are using the LED lamp, that is 9 watt. Okay, so drastic reductions of the energy, so that's good for your smart utilizations. Another thing is that transportations, you know that transportation, now sustainable transportations are happened basically. Now government also promoting to utilize lot of and using lot of EVs, okay, electrical mobility, sustainable mobility, as well as you know that for tractions, initially we are using for locomotives, we are using some diesel engines. Now that should be switched to the electrical locomotives, locomotives with the diesel engine. Okay, now it is totally electrical locomotives. So some of the portions, definitely it is reduce the energy, it is reduce that burning of the fossil fuels. Okay, also the consumptions, but most important thing is that waste management. Okay, so if we are using EV, whatever system we are using, so main important part of the system is that reliability. Okay, so who will provide us the reliability? Normally, if you are depends upon that renewable system, so most important portions of the renewables characteristics, okay, that is intermittency, means it can be vary with the time. Okay, so who will mitigate that problem? Okay, so mitigate that problem by the storage. Okay, so storage management is very important aspects for that system. Okay, so if we are dependent on the storage, so there are different types of storage. So in common point of view, if we are talking about the storage, we can understand it's a battery storage. Okay, so that can be used for the microgrid applications, that can also be used for that EV applications also. Okay, so storage, I mean, it's not like only battery, other storage also be there. Okay, supercapacitor, then spring. Okay, so there are different type of storage also, magnetic storage, that also be there. Okay, so but in normal cases we are using that battery storage. The problem with the battery storage is having some lifetime. Okay, so that then what happened, we have to after using of those storage, then definitely you know there is a waste. Okay, after some time that cannot be used, so it's quite generations of a huge waste. Like our you can see in your home there is a multiple numbers of mobiles. Okay, initially there is a desktop PC, now it has changed to laptop. Then you can see that e-waste such that after some years, after 5 years, 10 years, you can see there is a huge waste of the related products of the battery. So waste management, how they handle them, and the materials whatever we are using for the storage, that also consists of the heavy materials. Sometimes there is a lead, sometimes there is a lithium ion. Okay, so other heavy metals also be used for the as a component. So if we cannot drain them directly to our normal ground, if we are doing this, there is a pollution, soil pollutions. Okay, so that issues also be there, how to drain, how to reuse them. So that's why most important portion is that waste management. Okay, so these all are the aspects that can be that can reduce our overall temperatures of our environment, some of the percentage with our recent temperature level. Okay, so if you see the air pollution index in India, okay, so main point is that you can see a lot of pollutions from different country, different cities of our country, like Delhi, Lucknow, Hyderabad. Okay, if we compare with the China, they are having quite almost not 50%, almost 60% of the capitals. Okay, so in capitals, if we see in Delhi and Beijing, so you can see almost 60% of that pollutions of the Delhi. So air pollution is also be another important aspects for it. So we have to go for sustainable uses. Okay, so that's why government taking different schemes. Okay, so we are working on it also. Then we are talking about the microgrid. Okay, so different structures of the microgrid. Okay, here you can see the concept of the microgrid. So why microgrids? Okay, basically you know that microgrid concept is not so much new. Okay, that earlier it was there. Okay, right now also be there, and we are just reforming how due to the using of the systems, how the using them, that concept is going to be changed. Okay, so you know that first microgrid installed in India, I think it is 1983 in Sagardip. Okay, so it's based on the diesel based microgrids. Okay, means in it's known as Sagardip in West Bengal, Sundarban is Ganga Sagar. Okay, there is a famous mela in Ganga Sagar, that's Sankranti. Okay, so that was the first microgrid installed in India. Okay, so based on the diesel. Okay, diesel, and every evening time only 2 hours or 4 hours they're providing the power. Okay, now what happened? Now it was connected with the mainland through the transmission line. Okay, now it is not like a microgrid. So microgrid concept is not so much new. Okay, what is the concept of the microgrid? So if you see, when we are when the British government installed some of the power plant in our different parts of our country. Okay, so you can understand that should be the nearer to the base load. Two points they have mentioned: nearer to the river and the nearer to the base load. Okay, so that concept is there. Okay, so to provide the electricity, so local local in person as well as related to the industry person. And industrialization cities, they are nearer to the, they have installed the plant. Okay, that concept is like that base load. Now right now the grid system is there. Okay, it doesn't matter where the power plant is there, directly bus they have connected to the, all are connected to the bus. Okay, and you know that national grids are there, and that PGCI is also taking care about all those things. Okay, so how the microgrid concept is coming, it's also related to this kinds of idea. Okay, means captive generations by yourself only. Okay, microgrids, it can be categorized different parts. In my next few slide, I am discussing about them. What are the different categories of the microgrid? But thing is that we have to provide, we have to utilize some of the base load. Okay, by using our captive generations, it can be installed for our building, it can be installed for our locality. Okay, and it can be work in two types of mode: standalone condition or grid connected conditions. Standalone conditions, so here you can see that the different structure of the microgrids. Okay, so what are the important factors of the microgrid? So first factor is the energy demand, mean how much generations you have and how much utilization you have. The difference points, okay, the differences will be taking care about the taking care about whom? Differences taking care about your storage. Okay, so you can see all the cases we are using the storage. Storage is the important factors of the microgrids. Okay, whatever generations you have, the storage, without storage it cannot be work. Okay, and you know that another factors are there, that is monitoring, control and the balance. Okay, monitoring means what? That definitely the some of the portions, one two slide I am keeping here for that basic controls of the microgrid. Okay, so centralized control, decentralized control, okay, distributed control. So monitoring is required means how do you, is there any kind of fault, is the health of the health of the storage, all those things. Okay, so some scheme should be there for monitoring their monitoring monitoring the components, important components of the microgrids. Then based of the concept, based of the inputs from the monitoring system, we can control them. Okay, control them means what happens suddenly, any suppose we're having some planning. Okay, planning means every day we're getting this amount of solar power generations from our system. Suppose I'm taking on an example. Okay, suppose there is a dipping of that generation. So to whom means definitely if you having good monitoring system, directly you can will be taking care about that and providing the deficient power to the system. Okay, so that monitoring and control is important, and balancing means how the entire system is be balanced, an energy management system of the overall system, generation, demand, and how it will be working together. Okay, so these points are the very important. So then structure, you can see separate different structures are there. So microgrid, so first you know that this generations may be solar, photovoltaic, wind. Okay, and the loads, you know, that's EV load may be there, as well as building management means your residential load. Okay, and monitoring and control is done by that different, you know, that the IoT also very good concept. Now it is not so much new, it is almost 10 near about 7 years 10 years old concept. Okay, so IoT based control also been possible. Okay, and you know that if you require, so grid connected condition also be possible from the conventional generation system. Here you can see the utility grid, different types of load. You can see residential, commercial and industrial loads, and generations also be there, renewables also be there as per your required, and the utilizations. This is radial structures of the microgrids. Okay, based on that arrangement you can give some of the names. Okay, And now we can discuss about the basic what is the electrical grid. Okay, what are the concepts of the basic things? Some definitions are given here. So this is very simple thing. So I am not going to repeat them. Okay, all of you are aware about it. Now we are going to discuss about the classifications of the microgrid and how we can how we can classify them. Okay, normally microgrids can be classified into 5 parts. Okay, you can be classified the microgrid in 5 different way. Okay, what are the different ways are there? First, mode of operations. Okay, so based on that mode of operations, you can say like that it can be work isolated condition or grid connected conditions. Means means microgrid is working alone, then you can say like that it is isolated, and grid connected means and also connected with the grid. So there will be PLL and it should be the circuit breaker, then it will be connected to the microgrid, main grids. Okay, what are the different types of the microgrid? There are several types. First one is that DC microgrid, AC microgrid, and hybrid mode of operations of the microgrid. Both AC DC will be there. Then based on the source, you can also connect it renewables, diesel and hybrids. Okay, renewables means it can be different type of renewable sources, solar, wind, small hydro, biomass. Hybrid means that also hybrids mode of the different renewables. Okay, then diesel microgrid hybrid mode means it is renewable with the conventionals. Okay, that also called as a hybrids. And different load base means scenario based, residential, industrial and commercials. And size, based on your rating of the microgrid, you can also categorize into 3 types. That should be the less than 10 kilowatt, in between 10 kilowatt to 1 megawatt, and it can be the more than 1 megawatt. So these all are the basic classifications of the microgrids. Okay, as per their classifications, you can also categorize uh, nanogrids. Okay, then different nanogrids also very lesser dimensions of the microgrid. It can be below 1 kilowatt, or it can be below in between 1 kilowatt to 5 kilowatt also. Okay, so these all are the very basic classifications of the microgrids. Now, what I'm giving more focus on that DC microgrid. As we are talking about, we are using different type of different type of switching converters. Okay, so how the converters are connected with the system, how it is important. So DC microgrid means you can see here. Okay, the entire grid you are using, that it is in DC. Okay, so whatever generation you have, if you have solar generations, solar photovoltaic generations as a renewable, so we are using a DC-DC converter to feed the grid. As well as in case of wind, we are also using that generations of the wind happened in the AC. So there is a converter. There is a converter that is AC-DC converter and directly connecting to the system. So whatever your generations are there, but outcome, okay, outcome is in DC. Okay, and it is connected to the grid. And you know that it is a grid. So so that also related to, that also connected with the system. Okay, with which type of system? Storage. Okay, in storage, you know that there is a different type of storage, battery, capacitor, and sometimes electric vehicle storage also been used. Electric vehicle in your home, that is called that it also related to the bi-directional charger system. Okay, so suppose in night time, what happened in evening time, the peak demand of the load is quite more. Then what happened, your normal storage, suppose you are having standalone system. Okay, in your home you are having some standalone system. So you are doing some generation from the solar photovoltaic, and that energy is stored in the your normal storage system in your home. Okay, when the solar will be there, so that time the total battery bank, means storage bank, will be charged. And the evening time, what happened, then solar is not there, so it's like a UPS system in your home. So you are using that storage to feed the power to your internal, means to your home. Okay, sometimes what happens, suppose more demand, it is you have when you are purchasing the UPS or inverter for your home, so you have calculated the load, you are going to calculate the load, so based on that you are having some calculation. Suppose what happens, suddenly in any reason the load demand is quite high, so then what happened, your EV, okay, for the big durations, if you are having some EV, so EV storage also can be used, okay, to provide that additional power, to provide the additional load power, and it can enter to the system also. But all those things happen, but there is a basic problem with that, power quality issues. But all those things, power quality issues definitely will be there, but I am not considering the power quality issues for these aspects. Okay, so definitely some method also be there to taking care about the power quality issues. Okay, yesterday Professor Sujit Vishwas had also told about that some of the issues of the power quality and how would I mitigate that issue and how would I rectify the system. That also been discussed by the ISER. But it is a DC. Still, I am talking about issues, power quality issues. Okay, so it is a DC. So thing is that then your EV can also feed that additional power to the system to maintaining the balance of the stability of the system. So that's why sometimes we are working also bidirectional charger of that vehicles. So why we are also using the DC microgrid? So DC microgrid is not so much common. So main thing is another question is that if we are using the AC microgrid, that also coming in my next slides. So output of that any of the converter that is interfacing with your renewables, that should be the AC. Main problem is the synchronization. Basically, if we are converting to the AC, so if the frequency mismatching is there, they are having different ripple factors, so it is there is the issues of the synchronization. So okay, that's why if we are using the DC microgrid, then that problem will not be there. Okay, that issue is not be there, but other issues may be arised. Okay, so the system related to the DC microgrid, it may be the quite costly compared to the AC microgrids. Okay, so here you can see the storage management. Storage is there, battery, supercapacitor. It is high energy density. It is high power density for the initial transient or initial mitigations of the initial requirement of the power that can also fed by that capacitors. Okay, supercapacitors. Okay, here you can see is a another AC/DC converter. If you directly connected with your normal grids, means grid means supply. Okay, it's grids, so directly you have to connect conversions of AC to DC. So end of the day, you can see the outcome is the DC. That is your DC grid. If you are using different loads, AC load, DC load, DC load, so initially you have to incorporate some of the converters. For AC load, DC AC converter, DC DC converter, and DC DC converter. This is the basic layout of the DC microgrids. Okay. Now we can talking about AC microgrid. So if we compare both of them, this is a AC microgrid, this is an AC microgrid, and it's a DC microgrid. If we compare them, suppose we are having solar photovoltaic. Okay, both the cases we are having solar photovoltaic panel. So here you can see we are using DC to AC conversions. This is your AC bus and it is your DC bus. So it is DC to DC conversion. So all those things. Okay, so energy storage, wind turbine, whatever is there, so we are converting to DC here. Okay, and here we can convert to the AC, all those cases. Okay, storage is there, so we are AC. So load is there, so basic thing is that AC, and here you can see basic thing is the DC. Okay, this is the only difference of that AC DC AC microgrids. Okay, all those cases we are converting to the AC. Now if so additional conversions are needed. Okay, means if the generation is in AC, we are converting to the DC and fed to a DC microgrids. Okay, sometimes it is not so much good, means in point of that energy efficiency. Okay, so different stages of the power conversions. Okay, so we can give more trust on that hybrid microgrids. Okay, so in that case, you can see for hybrid microgrids, okay, we can also connect it. We can also connect that there are two buses. We can say like the DC buses as well as AC buses. Okay, here you can see it's and also the AC buses. It is your DC buses. So AC buses is connected to whom? The generations of AC like wind power. Okay, then diesel generator, biomass gasifier, okay, pico hydro, okay, whatever things, whatever AC generation, still there. Okay, so AC to AC conversion definitely will be there, but and the grid, if we connect it, it's in circuit breaker. Okay, so whatever things are there, so we can directly connect it to the AC. And there's reversing also there. So battery storage, the outcome of the storage is DC. So we can use some DC-DC converter and connect it to the DC. So some loads also be DC loads can be connected to the DC bus, and other sources photovoltaic that can be considered. So there are one another converter that is called AC-DC bidirectional converters. It also known as the it is also bidirectional inverter or the interlinking converter, that can also known as such a manner. Okay, so what we can do, if more load is there in DC loads, more load is observed in the DC bus, then what happen, additional power will come from your AC bus to DC bus through this converter, then that converter is working AC to DC converter. Okay, the reverse thing also will happen if you are having more load to the DC AC side and more load to less load to the DC side. So additional power from come to the converter from DC. At that time it can be work as an inverters like DC to AC. Okay, so this bidirectional power flow can be possible in that hybrid microgrids. Okay, so it's look like very very good that it can be work proper manner, but the problem is that it is not so much simple manner. The control logic is going to be quite complicated in this case. Okay, so there are two converters, you know, that is one is main converter, another one is for auxiliary converter for backup purpose. Okay, so there are different pictorial representations for architecture of different AC/DC hybrid microgrids. Okay, so here we can see AC microgrids and DC microgrids different. So in that case, all those things connected, like your solar photovoltaic is connected here. Okay, through the converter. Okay, means AC to if it is your if it is AC microgrid, so converted to the AC and connected to the AC grid. So both the way it is possible. Okay, so it can be shown like that way. Different pictures I have given, I have inserted to understand all those things. Okay, so by the converters. Okay. Now different functions of the power electronics interfacing module. Why that power electronics, that the title is that switching converters. Okay, so it's related to the design of the switching converter, why they are important. Now you can see different ideas from that different types of microgrid, so we can understand that interfacing of the renewables to the any of the grid, any of the microgrid, AC or DC or hybrid. So power electronics converters are the mandate points. Okay, means we are interfacing we are interfacing the renewables to the grids through that power electronics converter. Okay, that's why we can say like that. That's power electronics converter as an interfacing applications. It can be work different conditions. So for the interfacing purpose, first case. Second case is that it can be also used for that bidirectional operations. Means there are two types of bidirectional operation: DC-DC bidirectional converter for normal battery storage to our basic grid. It can be also work. Some of the power electronics converters can also work that DC-AC, AC-DC, sorry, DC-AC bidirectional inverter also. Okay, so different aspects, different applications it can be used. That's the importance of the switching converters or the power electronics converters. Okay. now different protocols and the standards that we are talking about the power quality issues. Okay, so definitely if we connecting the components with the system. Okay, so power electronics converter, if it's connected to your system, definitely it will provide you some nonlinear oscillations. Okay, then generations of the harmonics. So definitely the power quality issues will be arise, and that can increase the TSD level. Okay, so we have to be planning for different filters. Okay, to how to mitigate that power quality issues, and we have to maintain the IEEE standard. So whatever we have designed, okay, suppose we have designed one topology and implemented like that. Okay, I have proposed something. Okay, but if it is following the criteria of all the standards, so who are providing the standards, there are different standards, that international standards, our country, in case there is some codes, electrical codes. Okay, so electricity codes that we have to follow, and normally in international level what we are following the IEEE standards or IEEE protocols for how much TSD will be there. Okay, how much local factor. So all those cases we are having some protocols, so we have to follow the protocols to designing our product. End of the day, main target is to development the products. Okay, whatever that's good, no problem with that one, but how practically it is working and how feasible is it for the practical aspects, that should be the main aspects for the development of the product. End of the day, whatever we are telling that we are using for our domestic purpose, the main motivation is that what where main planning or motivation is to install the system for our daily uses. Okay, so for our regularly uses applications, if it is not following the protocols as a product, so that should not be acceptable from anyone. Okay, so that's the features, that's the factors to maintaining the protocols. Now we know that why that switching converters. Okay, so you know that if we are designing the power electronics converters. Okay, so we're talking about different types of converter like buck converter, boost converter, buck boost converter, means different examples for the DC-DC converters. Okay, that portion is basically especially focused on the DC-DC converters. Why DC-DC converters? If we working commonly. Okay, so I am commonly working on that topology, means suppose you are having some DC generations and you are giving to that outcome as a DC outcome. Money as the input is a DC, output also the DC. So power processing unit, it's a DC to DC conversions. Okay, so you know that first thing, the title of the presentation is switching converter. Okay, what is the switching converter? So you know that there are different DC to DC conversion, it can be possible in different manner also. Okay, switching means there are different type of converter, like suppose linear converter as well as the switching. In case of linear converter, what happens, the solid state device, whatever, suppose we are using the MOSFET, we are using the IGBT. Okay, as per the applications. Okay, so applications of the it depends the rating of the system and the specifications of the system. Okay, so how much, if we need more switching frequency, we can also use the MOSFETs, power MOSFETs. But in case of linear converter, whatever solid state devices we are using, that is not that can be work as an active zone operations, means it can behave like a variable resistance. Okay, that's why there is a huge more, so more heat will be generated. So for that mitigating more heat, we have to incorporate big heat sink. Okay, if you incorporating big heat sink, means definitely it will be in bulky in nature, so the thermal efficiency is not so much good, means definitely it will reduce it, the costing will be increased. So that's why what we are doing, we are switched to the switching converter, means that solid state device is like a switch, either it will be on other means saturation region or the cutoff region, that we are avoiding the linear mode of operations. Okay, so so if you multiply them, so you can see that's a 0. Okay, if it is current is high, okay, so voltage is 0, means short circuit. Okay, and open circuit condition, voltage is high but current is zero, so multiplication is power is zero. So now also the sub switching concept also be there. Okay, so that's why we have switched to we are moved to the switching converters. Okay, but problem is there if we are talking about the switching converters, and it's also an power, also a power electronics converter, it having problem with the switching non-linearity. There are different types of non-linearity. You know that in control system we are studying on it. There is a backslash. Okay, so there is a dead zone, then limit cycle. So different non-linearities are there. Okay, so the problem is there. Switching non-linearity also very common in our power electronics. So what is switching non-linearity? That is switch on, switch off, switch on, switch off. So that is also non-linearity. It is called switching non-linearity. Okay, so that's why if the non-linearity will be there in the system, so when we are talking about different control, you know that currently you can see different literatures, they're using some very sophisticated controllers and very complicated controllers. Suppose you know there are different category of the sliding mode controls. Okay, different levels will be there. Levels means different topologies of the sliding modes also be there. Adaptive control, then some mathematics involved with that system. Okay, so if we designing all those things in the control system aspect, so we have to design our power electronics converters in that point of view. Okay, means mathematically we have to convert them in as per our control rules, means whatever control rules are involved with the system, so it should be implicable to our power electronics converter system. That's why we have to convert the power electronics model in the point of view the mathematical aspects. Okay, and basically you know that right now all the controllers whatever we are using, okay, so it will be in inbuilt with the sometimes digital simulators, or you can see you can also writing in the form of code in microcontrollers, okay, or the DSP processors. Okay, so that we are getting every day different advertisement than in our TV. So intelligent system, now you know that by only the IoT based control of the fan, then smart lighting, means all the processing is involved with some processors. Okay, analog control is very good, there is no doubt on it, but still that digital control is already there with our normal products. Okay, that's why if we implement kind of sophisticated control, so we have to convert our system as per our requirement. So here you can see that the first requirements. Okay, so what is the motivations for that work? Okay, so first we have to fix up their motivations and we have to select the topology of the converter. So topology of the converters, normally there are two points. One is that if we see the dynamics of the system, dynamics of the converter system, so you know that there are two types of thing. One is another one is the steady state characteristics. So normally transient characteristics, okay, that control, that is controlled by the controlled by the controllers. Okay, whatever controllers you are using, that can decide the transient behavior of the system. And the steady state concept is the steady state behavior normally decided what type of topology you are using for it. Okay, so why it is important, why, what do you mean by the transient and what do you mean by the steady state? Okay, normally if we see if you are realizing the control system structure, okay, so you know that open loop control and closed loop control. In case of open loop control, we are normally doing in the form of that is called identifications. Okay, so if we know that there is some experimental setup in our UG laboratories. Okay, when we are in our UG, so we can see the identifications of our physical system, just what kind of system we are using, electrical heaters. Okay, okay, so we are designing the different parameters like Kp, Ki, okay, and Kd. for the ZN method, by using ZN method. In that case, what we are doing, we are using the identifications of the physical systems, means we are varying the inputs. Okay, like our hysteresis graph. Okay, so we are giving gradually increasing the input and try to realize the system behavior, how it is starting. Okay, then starting portions, then it is going to the linear portions. After sometimes it is entered to the non-linear portion, means saturations portions. Same thing also happened with our any of the physical systems. Open loop, we are studying all those. Okay, then what happened? We are find out the linear mode of operation. Which portion is linear? We are working only that duration, and we can go for directly closed loop control. In closed loop control, what we are giving? Normally, we are giving some reference. Okay, and that is called the set point tracking. So reference, if we are giving, then there is a changes in the reference. Okay, changes in the reference means different kinds of changes can be possible. That also is related to our control system or circuit theory. Okay, so network theory system. So you can see there are different type of signals: step signal, unit step signal, ramp signal, impulse signal, sinusoidal. So all different kinds of signals we are understanding as an input. So such type of thing, if we are giving as a reference, and we have to see how our output is coming, means output is following as per our reference or it is not coming as per our reference. So if it is coming as per our reference, we can say like that our system is properly guiding. Okay, properly guided as per the reference signal, and who will taking care about all those things? Taking care with all those things. Now, what is the response time? Suppose there are several types of controllers. So why we are going, the PI is the most commonly used controller. Okay, and directly also some, now I am talking about that persons are also using the sliding mode controller for the complicated drives also. Okay, means it's very sophisticated control and you are using in different machines based system. Okay, so what is the difference on it? So if you see that mechanical inertia of the machine is definitely it's high. Okay, so if any disturbances happen, okay, if any disturbances means what? The system face some additional problem. Okay, additional thing, suppose in form of the electrical point of view, there is some load. So suddenly the load is increased of the system. Okay, then what happened? That we are already talking about the conservation of energy or the power. So power is fixed. Okay, power is fixed. Suddenly load is increased. As an electrical engineer, the load in the form of, definitely in the form of current. Load is increasing, current also being increased. So if we want to maintain the power fixed, then what happens? Voltage will be dipping. Okay, so then how would I mitigate the dipping and how fast again the voltage should be the rated value? That will be taking care about the controller. And that is your transient response. So how fast it is mitigating by the controller. Okay, that will be decided. How fast it is mitigating the problem, that will be decided by your controller. That's why the transient performance always related to the controllers. Okay, so that's why all the persons are using different types of controller for their work. Okay, and steady state performance means what? We are having some, suppose I am talking and taking an example for a boost converter. Boost converter having one inductor. Okay, so it having some ripple. Okay, so current is rising up, again switching of condition, current is rising down. Okay, so it having some ripple. Okay, and you are having some interleaf boost converter. Okay, so not like only boost converter, buck converter it can also be happen, buck boost converter also can be happen. So now we are changing the topology from normal boost buck or buck boost to interleaf conditions of the boost or buck or the buck boost. Okay, so what is the concept of the interleaving converter? So there is a 180-degree, suppose it is two phase, so 360-degree divided by 2, that means what? It is 180 degrees. So it is not a parallel operations. Okay, so there are four modes of operation if you are having two phase interleaf converter. Okay, so I'm considering it is 180-degree phase difference is there. Then what happened? So you can see there is a chances of the ripple cancellations. Okay, Okay, so you can see the input currents for the boost converter having more ripple compared to the input currents of an interleaf boost converter. So what we can conclude from the statement, so steady state response can be decided by the topology of the converters. Okay, that's why all are important. Okay, so first we have to select the topology of the converters. Okay, so as per our requirement, arbitrarily we cannot do anything. Okay, as per our requirement, we can fix up the topology of the converter, then mathematical modeling. I hope you can understand why mathematical modeling is important. So it having some nonlinearity issues, okay, practically. Now you have to realize the same thing in our mathematical aspects, as your controller is totally based on your mathematics. Okay, so you have to imply or you have to replicate the entire topology in the mathematical. So mathematical modeling is very important, but problem is that there are different types of mathematical modeling. So if we're going for the switching converter, we are having average modeling methods in any of the standard power electronics book. Okay, you can also see normally we are using different modeling, canonical modeling, then average modeling also related to the canonical modeling, then state phase average, state phase modeling, state phase averaging is there, as well as another modeling is there, state phase modeling also there. Okay, so both the cases we are doing the averaging, but if we go for more accurate results, we can switch to the Philippa methods of the modeling. Okay, now other type of also modeling also be there. Those are working in the non-linear dynamics portion, means they can study in the chaos. Okay, so studying the chaos is not only the power electronics converter. It can be happened. It's very common studies for any of the physical systems. Okay, the mathematics person. Okay, they are working on it. So electrical system is very good. There is a special power electronics converter is a very good scope to working that to understand that type of dynamics for our system or that type of concept. So mathematical modeling also important. How do replicate the system in mathematical point of view? Then control systems. Okay, control system means now what type of controller you are required. You are using. Suppose you are having you are having renewables as a input, as an input. Okay, so what happens? So intermittency is the common factors for the renewables. So what you need to do, we have to design some adaptable controllers. Okay, to controlling the power converters that is associated or that is interfacing with your renewables. Okay, so control scheme also important. For the control scheme, the mathematical modeling is more important. Then we can go for the implementation. Implementation having two parts. First, we can do that software verifications. Okay, after doing the software verifications, we can send it to the PCB. If you want to do in PCB layout, so then PCB layout you can prepare. Then fabrications, finally testing you can do. Then it can form as a product. Okay, so after doing all those steps, okay, we have to in the testing lab, what we need to do, we have to study different points. So that is line regulations, second one is load regulations and transient response, and finally the stability analysis. Okay, so line regulations means what? So if there is any changes of your input side with the controllers, okay, how your output is making fixed up. Suppose input side any variations are there. Okay, it's not like the abrupt variations. There is some limitations. Definitely tolerable band will be there. It should not be more than 5%. How your output is changing. Okay, so practically in simulation anything can be happen, but practically how it is implemented, how it is changing, how much value, that you have to study. Okay, to you can to define that how much percentage of line input variations can be tolerated by your design product. Then the load regulations means suppose in load side also with the variations, with the presence of the disturbances, it can also be changes. So with the changes of the load side, with the disturbance of the load side, how the output is, how much output you are getting, how it is steady value or not. Then transient response also be there. Okay, that's based on the controller with the different disturbances, set point tracking, disturbances is in control input. Okay, and different type of disturbances can be possible. step, unit step. Basically we are using unit step or step disturbance, staircase disturbance, okay, ramp type of disturbance, okay, based on your applications, okay. And finally stability analysis, with the changes any of the disturbance, how your output is stability, okay, and it is fixing up or not, that is another thing. Okay, now we are using different that we are talking about the mathematical modeling, okay. So there is a, we have already told about the non-linear time varying system, switching only it is there. So state phase averaging method, that is very common modeling method for designing the converters, okay. And let's say there are different steps, okay, for state variable analysis for each of the circuits. So on state equations, off state equation, then output equations for switch on condition, switch off condition. So first we are getting that state equations for switch on condition and switch off condition, switch off conditions. Then what happened, we are averaging them, okay, duty weighted averaging. So averaging the state variables by using the duty ratios. Okay, here you can see that on state equations and off state equations and combining, this is your state variables, okay. And it is also for on state, this is for off state, and it is output equation, okay. Then what we are doing, we are averaging them, then we are doing the perturbations, okay. Perturbations means if you have state variable, there is a two factors. One is your fixed value, that is your DC component, another is small varying components, it is your AC value, okay. Then we are splitting an individual factor is splitted, okay. So all the factors are splitted, it is written in lowercase italic factors. So that means we are considering it is an AC value. Now that value is uh, instantaneous value. So that value is splitted with two portions. One is your DC component and small AC component. Now we are splitting them. The DC component we have splitted as well as the AC component. From the AC component, from the DC component, we will get the steady state value, and from the AC component, we can get that. Finally, finally, what we will do, splitting them the DC and AC. Okay. Then AC component, what we will do, we are doing the Laplace transformations. Okay, Laplace transformations. Then what we will do, that inverse Laplace transformations again. Okay, then Laplace transformations, then we will get that control to output transfer functions. Okay, so control signal to output signal transfer function, we will get it. So here if we see the basic block diagram, it is very common diagram and available any of the power electronics, standard power electronics book. So it's your reference. So it is your controller transfer functions. Now there is a two portions, one is PWM controller, that is DCC converter. So there it is your total transfer function is output by control signal. This is your control signal, and it is splitted to the duty to control signal and output to duty. So if you get the output from here, okay, so that output is going to be there as a negative feedback to the system. Then what happened? It is compared with your reference voltage. Okay, whatever output is there, it is coming and compare with your output voltage. Then what happened? We will get some error signal will be there. That error signal will be passing to the controller. Then after passing to the controller, we will get the control signal, and that control signal is controlling with the repeating sequence. Okay, it may be the sawtooth, it may be the triangular one. Then after comparing that value, we will get some duty cycle. Okay, that duty cycle will be fed to the switch. This is from the control circuit. Okay, and this is from power circuit. So then that can be that PWM will be floated to the driver, meaning actually actuator, and actuator driver. Then it will be drive the solid state device of your couple of the converter switch. Okay, that's the way. Suppose I'm taking some example. Suppose there is a high load. Okay, suddenly it's an equilibrium condition. It is working fine. Suddenly, what happens? Some load has increased. Okay, suddenly the load has increased means what? Then suddenly the current will be increased. Okay, if the current is increased, then what happens? Voltage will be dipping. If the voltage output, which voltage? Output voltage. If output voltage is reducing, dipping, means what happen? That directly then what happen? Then error will be more. Okay, as it is compared with the reference value, as we are doing the reference voltage tracking, so error will be more. If error will be more, then what happen, it is passing to the controller, so that value, that VC value, it will be more compared to compared to the first conditions. That means what happen, if there is a error, okay, so there is a error, okay, so suddenly what happened. Hmm. Okay, suppose we are having that initially we are having that error signal, okay, means control signal, and we are comparing with repeating sequence. Okay, now what happened, now error is more, so definitely that value will be shifted to high. Okay, so we are considering that we are fixing up the logic such a manner. Okay, we are fixing up the logic such a manner when the control signal, this control signal is more than your repeating sequence, that will be your PWM. Okay, now what happened? Error will be more. So error will be more means your control signal is shifted from initial point to this point. So if we compare with that repeating sequence, okay, then you can see you are having more pulsing. Okay, you can see that more pulse rate. Initially it was your off time. Okay, your initially it was your off time, that is your off time. Now your off time is less to this value, reduced to this value. Then what happened, your switch will be turn on period of the power electronics converter will be more, so voltage automatically regulating that fixed value. So we can say like that, we can tell like that, so it is maintaining the stability. Okay, it is working fine. So now we are talking about that interfacing converter. So in solar photovoltaic, we are using the feed forward control. Okay, so it's your normal DCC converters. Okay, it can be you are using if your generation is 12 volt, if it is required in 48 volt or 24 volt, whatever. Okay, so for suppose 24 volt, so what you are doing, you are stepping up the value. Okay, so you can use some the boost converter, but normally we can also use the SEPIC converters. Okay, SEPIC converter, Chuk converter, that can be also used. In case of Chuk converter, polarity may be opposite, so we are using the SEPIC converters. So for getting more gain, so you can also use the isolated converter also. Okay, so we're using that MPPT algorithms. Okay, there are different types of MPPT algorithm available in the literature. So based on that, we're using the MPPT algorithm to getting that voltage and current of the panels, and we're using there's some calculation. Algorithm steps are there, calculating power for with MPP points, and we're varying the duty cycles of the boost converter, getting the output response. Okay, that's a very common example. So what are different types of MPPT, so I'm not going to discuss on it, so it's very common. Okay, now most of the person are working on it. Okay, so that's the way. So applications, whatever we are talking about, that boost converter, so this is a converter we can use as an interfacing converter for the solar photovoltaic. Now we are talking about that modeling. Okay, so that first case we are talking about that closed loop option. So now how it is related to the boost converter. So it is there is a mode on operations, that when the switch is on conditions, and mode to operations when switch is off conditions. Okay, so these all are the state equations. By first case, what are the state variables? We know that's the minimal number of states, that can minimal number of variables that can define the states of the system, that is known as the state variables. Okay, so in case of boost converter, two energy storing elements are there, that is L and C. So we can say like that inductor current and capacitor voltage, both are the state variables. So we are using the KVL and KCL to find out the state variables. Okay, and both the cases for on state on conditions and the off conditions of the switch. Now what we will do, we are averaging the same thing. Okay, here we are averaging for on averaging for this is your on time, this is your off time, and enter the switching time period. So we are averaging them for the state variables. Then what we will do, this is for we'll do, we are having the standard equations that previous few couple of slide back we have discussed. So directly we can find out, means after using the perturbations we have some formula, directly we are placing that a1 into value, and we can get the Planck transfer functions of that boost converter. From the transfer function we can see that one RHP0 is present in the boost converter. So what will be the problem with that? So it is an example of a non-minimum phase problem. What do you mean by the non-minimum phase problem? So if we see, there is a contributions, it is a second order system and two poles are there. There is a two roots in the denominator, so that can contribute minus 90 and minus 90. If one zero is there in the right hand plane of the plant, so that can also contribute minus 90. So it is coming minus 270-degree phase delay. That's why it is called that non-minimum phase system, means maximum phase delay system. Okay, so what will be the problem with that one? So problem is there. So if we see in open loop system, okay, if we see the step response for the open loop, okay, so we can see that initial undershooting is there in case of boost converter. The same features also happen for the buck boost converter also, and the derived converter based on the boost and buck boost, all those cases this problem will be there. So normal PI controller or PID controller are not able to rectify. It is not called the rectify, are not able to provide the satisfactory results with that problem. Okay, that's why we have to fix some special type of controller that is called type controllers. Okay, that will be there one slide on that I'm giving. So similarly, we will do the same thing for the buck boost converter, on state equations, off state equations. When we are doing the averaging that value, okay, finally we will get the transfer function, Planck transfer function, control to output Planck transfer function, the buck boost. The same problem also be there in right up plane 0, same problem also be there in case of buck boost converter. Okay, so again it's a non-minimum phase problem. Okay, based on that problem, again that undershooting will be there in the response. So that's why what we are doing, we are using different type of converter. So type 1 converter, type 2 converter, type 3. What is type 1 controller? So it's not like that in our control system thing that how much number of poles at the origin, is not like that. So name is like the type, but it is actually only type 1 controller is an integrator. If you see the structure of the controller, it's look like that only one capacitor is in your feedback path. So it's an integrator, an example of a type 1. So what is type 2 controller? Type 2 controller is an integrator cascaded with a lead controllers. Okay, so why lead controller? Okay, integrator portions can think about your reduction of the steady state error. Okay, and lead controllers also providing some phase boosting. Okay, there are, you know that in control system, lead controller, lag controller, what are the dynamics of the lead controller, like means Bode plot of that one, how it is lead controller having phase boosting capability. Okay, that's why we are using lead controller for mitigating that phase lagging. Okay, there is a non-minimum phase, so inherently it is 180-degree phase delay. So if we are providing the phase boosting to the system, so that's why we are using lead controller. So lead controller having so it can phase boost up to 90%. So and sorry, type 2 controller can phase boost for the 90%, and so that's why we are using the type 3 controller. Okay, so it's an integrator, then two lead controllers. So lead integrator plus lead controllers. Okay, so it can having the capability to phase boost of 180 degree. Okay, so why we are using, main thing is that for getting better transient response. We are talking about what? We are talking about how would we get the better transient response for our system. Okay, so if we are and controller only take care about the transient response. So if we are using lead controller, so definitely if we are using type 2 and type 3 controller, definitely we will get that better response. Okay, so that's the motivations for this work. Okay, and you know that boost, buck boost, and say peak Jita and as well as the Chook, all are the well-known interfacing converter for solar photovoltaic as an interfacing case. So definitely the dynamics will be there. Okay, so if we see at that point of view, definitely that problem will be there. So we can overcome by using this system. Instead of PI controller, we can use this type of controllers. Okay. Now that we are talking about different types of other switching converters, so another thing is that tri-state boost converter. Okay, so that we are talking about what for the boost converter there is an issue of what there is an issue of non-minimum phase problem. So non-minimum phase normally happen for the zero, and that zero is normally coming with that the presence of that inductor. Okay, so if you see that's energy charging capability of the inductor, that directly it's having directly relations with the zero, and that's the main effects. Okay, and that if we changing that value of that switching frequency, so we can also having the place of that zero for the boost converter. Okay, but main problem is that inductor. So energy charging capability of the inductor, that's the basic issue. So what we will do for the tri-state boost converter, we are incorporating additional state. Okay, additional state means boost converter is working two modes of operations. One is the mode 1 means switch on operations, mode 2 switch off operations, and tri-state boost what we will do switch on operations of the switch, this one, switch off operations of switch on operations of this one, then switch off operations of this MOSFET. Okay, and switch on operations of this MOSFET, one SF, and many freewheeling MOSFET. So another path will be there. Okay, across your inductor for freewheeling that energy. Okay, that will be dissipating through this path. Okay, so what happened we can understand is a you can see it's a pattern of the steady state pattern of the inductor voltage. Okay, so it you can see on zero, that is zero axis, it is zero, so that portions the inductor voltage VL is zero. Okay, it get pulse or steady state current, and you can see that current is flowing, it is freewheeling current. Okay, with the gate pulses are there, two gate pulses are there. Okay, and is the structure, it's analog control. Okay, so it can also be done for the digital platform also. You can use that DSpace. Okay, you can use other oscillator other uh, digital platforms. Okay, so DSP processor or microprocessor based thing I'm not doing on this one. Okay, we are using some analog control. Here you can see the analog control structures. Okay, so it's a power circuit, then current probe, so we can understand. So changing of that variations. Okay, load disturbances, we are see how the output voltage is coming. First stepping up voltage, stepping down voltage, it is coming for the tri-state boost converter with step load resistance changes. This is your type 3 controller. Okay, and it's comparators. Okay, it is generations of the repeating sequence. Okay, like that, triangular function generator actually. Interleave boost convert. So we're talking about just starting up that initial slide of the session, that what is the importance of the converter topology to maintaining the steady state value. So boost converter, what happened only that it is your inductor current. So it is your inductor current. We are using two switches. They are using interleave conditions. Okay, two switches are there in interleave conditions. So switch on and switch off. Switch on and switch to. Okay, so they are in interleave and two phase. So two phase means there is a 180-degree phase delay. So you can see that inductor currents. Okay, for their 180-degree phase delay. Okay, one is saffron color, another one is that magenta color thing. Okay, so they are in that directions, in that way. Okay, so they are encountering each other, so there's a ripple cancellation. So you can see for input current here, if you see the input current, it having lesser ripple with compare the one inductor current. One inductor current is ripple more than your input current. So in case of boost converter, what happened? Only one inductor current. If you see here, that is your that is your input current. So in this case, you can see the lesser ripple, input ripple. Okay, for that interleave boost converter. So it is much more convenient than your normal boost converter. Also, it having more current carrying capability. Okay, so that's why the topologically will get the better steady state response. Okay, so same problem also happened with that interleave boost converter, as it is derived from the boost converter, so it should have the non-minimum phase problem. Okay, so here we are observing that step up and one staircase type of it is step down then step up type of load when a load is disturbances are there, and we can see the current variation. So load is reduced okay, voltage disturbances are there. Okay, voltage disturbances are there means voltage is suddenly reduced. This is disturbance voltage, so it is having some value, suddenly it is zero, so load current is increase. Okay, so that's why you can see input current is also varying, phase current also be changes, but output voltage is regulated. Okay, the disturbance applied these 2 points. Okay, I hope you can understand. It is also using type C controllers. Okay, so two comparators are there and the function units also be there. We are using the analog control here. Okay, one is load resistance, another one is disturbance for the resistance. Okay, now we are using that tri-state interleave boost converter. Okay, so that interleave boost converter having non-minimum phase problem. That's why what we are doing, we are cascading the tri-state and the boost converter. Okay, both were connected in the interleave point. So we're getting this kind of structures. Okay, and the steady state response also be there for the interleave boost one that for the tri-state interleave boost converter, and the comparison also be there. You can see that medium money it is for tri-state boost conference input current ripple, and it is for interleave, so we are getting the in between response, so it is satisfied. Okay, simple thing, I hope all of you are able to understand. And now we are talking about the DC-DC bidirectional converter. So bidirectional converter having some DC grid. Okay, and you are having some you are having some DC generations and battery, or you are having some DC grid. Okay, so if your battery voltage is more than of your DC bus voltage, okay, then what happens, battery will be discharged. Okay, so if it is more than of your bus voltage means, how is it working? It is step down condition. So battery will be discharged through the buck mode of operations. If your bus voltage, DC bus voltage is more than of your V battery, battery voltage, so battery will be charged from the DC bus. Okay, so how it will be charged? So it is working as an oh, sorry. I have actually charging from what? From if your input voltage is more than of your output voltage, so it will be discharged to the buck mode operations. And your input voltage is less than your bus voltage, then definitely it will be charged. Okay, so definitely it will be the boost mode operation. So here you can see battery is there and boosting is there, DC link voltage is there. Okay, and both, and this is your DC link voltage, this is your battery. Okay, this is your buck mode operation. So what we will do, we are just connecting them, we are clubbing them, then what happened, the switches are there, both the cases the switches are there. Okay, so it initially is unidirectional switch, now it is your bidirectional switch. Okay, so bidirectional switch is there means automatically bidirectional flow of power can be possible with that one. So this is the basic motivations for the bidirectional converter. So there are different topologies of the bidirectional converter. The details thing will be discussed in the next sessions after my session by Professor Indrajit Sarkar. Okay, so that I'm giving the very basic preliminary of the bidirectional converter. Okay, then converter. So you are getting DC output as well as the AC output. Okay, this is hybrid converter concepts. Okay, so whatever input you have given, you are getting two of the output. Okay, so it having some structures on that. Okay, for the hybrid converter, so multiple conversions will be there. Okay, so multiple conversion may cause for energy losses again. Okay. having some applications. Okay, so now almost most of the theoretical thing we have discussed. What is our motivations? Okay, now we are giving some of the applications for the for our study. Okay, what we have done. So we are talking about different bidirectional converters. So first we are considering one basic solar photovoltaic system here. So MPPT circuit will be there. It's a feed forward control and it's a DC bus and DC loads is there. Okay, so what we will do, so we are having storage. Okay, so you can see that so what we will do, it is our bus voltage and reference bus voltage here, and whatever bus voltage we are getting, so we are using two controller. One is voltage controller, then we will get the PWM. So two loop control also be possible. So here we are considering the one loop of one loop, two loop also be possible. So by that way we are having some standalone system, and we are checking how much output we are getting with the system and which type of MPPT. Normally by default we are using the P&O algorithm for the MPPT applications. Okay, so what we have observed from the study, from the simulation, so solar photovoltaic operation is there, MPPT under different operating conditions. So here we can see the using the voltage controller. Okay, using voltage controller, whatever we are getting more or less fixed voltage, initially transient is there, and without voltage controller we are getting that green color of line. So here we are observing that IV characteristics with for 1000 watt per meter square irradiance, and that and its IV characteristics for 25 degrees centigrade, PV characteristics for 25 degrees centigrade. IV and PV characteristics for different conditions. Okay, we are getting from here. So we're plotting the responses in the MATLAB. It's common thing. Now we're talking about that it's a bidirectional converter. Okay, so V bus and this is your V battery. Okay, so we're doing the two mode of control. First is voltage controller, another is current controller. There is a difference between that voltage controller and current controller. It is timed, that is time constant will be difference. Okay, that is more faster. Okay, the current controller is more faster than your voltage controller. Okay, so differences are there, then we will get the error, then error passing to the voltage controller, then current differences is given, then we will get the PWM, and that will control the S1 and S2. Now we are cross-checking the system that it is working fine or not. Okay, so we are cross-checking the system and different conditions we are observing that how is it working. Okay, for normal standard conditions. So we are using that. So we are using some set phase average modeling, okay, for getting the transfer functions, and we're getting the controller designing by using the CISO tool. Okay, so normal PI controller is using for the study. Okay, so and here you know that values of PI controllers are given. So CISO tool you're using auto tuning. By using that CISO tool we can also tune, first getting some value from the auto tune, then we can change the pole zero locations and we will get that better response to controlling the system. Okay, so here we are having the parameters for the voltage controller and current controller parameters. So initially we can see the battery characteristic, different mode of operation. So battery is charging means current will be negative. Okay, so zero means it is okay, then it is discharging. So when it is charging, so it is rising up. Okay, then discharging is rising down, and current and voltage all are complementary. So current is it is charging means battery voltage is high. So if we multiply them, then we will get the battery power. So initially battery power will be negative. For this condition the power is 0, then it will be again changing. Okay, so it is positive. Okay, so like that it is changing like that way. Okay, voltage and current both. Now there are four conditions we have considering this one. Islanded condition of the DC microgrid with the solar photovoltaic. So first one is the solar power generated by PV, P load with the load power. Okay, so there are four modes of operations. Mode 1, when the PV power equal to PV load, there is not a presence of the storage. Second condition we will check for PV means PV power is more than your P load with storage. And mode 3, when PV power is less than your PV load and it having some storage. And mode 4 is when PV is varying. okay, with the storage, and how the responses are coming, how is it behaving, that we need to check here. Okay, so first conditions, mode on operations. So what we will see for more money conditions one, PPV equal to P load. If the load is sorry PPV equal to P load without storage. So whatever your generation is there and your load, okay, load also be maintaining. Okay, so voltage variations with the load. So directly if it is load is changing, so definitely voltage will be varying. Okay, so the system is the irradiation and ventilation purpose. Now the condition 2 for the buck mode. So PPV is greater than P load. That means what will be the additional power will come from whom? Come from the storage, means battery power. So P battery equal to P load minus PPV. So here you can see the generated power by the solar photovoltaic. Okay, so power generation almost constant over there. Now load power is there. Okay, so additional load power is increasing. Here you can see the load power is increasing 5,000 nearer to the 4,000. Now it is 6,000. Then it is nearer to the 11,000 like that. Okay, so you can see the battery power. So initially what happened? Battery is charging more. So battery power is negative. Then it is additional. You can see it is following that thing. So it is coming. Okay, to that one. So PPV is more than the P load. Okay, so additional power to where it will go? It will goes to the battery. So that's why initially battery is charging. That's why battery power is negative. Okay, so then it is gradually come to zero. Okay, if the reverse thing happens, so battery will be discharged. See for buck mode of same, so battery is charging means it is buck mode of operations. Okay, so here you can see the battery current, initially current is negative, so gradually the negative is less, then it will be zero. SOC also increasing like that way. Okay, so here you can see the battery voltage, initially voltage is more, then reducing current, battery power should be constant. Okay, so if current is increasing, so voltage will be decreasing like that way, and you can see the variations of the load with the battery. So voltage variation is constant almost. Okay, so voltage and the grid increasing with the load. It is for the characteristics for mode 2, condition 2. For mode 3 operations, it is boost mode operation when PPV is less than of your load. So load is more than your PV. So additional power is coming from whom? Additional power is coming from your storage, means battery storage. So you can see the generation is constant almost. Okay, now load power is increasing with 2 seconds. You can see it is increasing, so power is coming from the battery. So it is initially with the same, then what happened? Here you can see the additional power here, so it is coming from the battery. So that's why battery power is positive, current is positive, voltage also reducing, but it is in positive, so positive power. Battery again it is positive, so more power you need to deliver to the increased value of the load power. Okay, then battery current is 0, then it is positive. Okay, then SOC level due to the discharge, so SOC level is reduced. Battery voltage also reduced, but voltage variation with the load it is fixed. Okay, so this is the condition 3, and finally, so this modes the variations of the solar irradiation, means solar photovoltaic variations also being changed. Okay, generations of the solar. So the photovoltaic it is changed, load power it is maintained fixed, battery power, so additional power is coming from the battery, initially negative when charging of the battery, then it is discharging. Okay, when you know that first irradiation is there, then irradiation is reduced. Irradiation reduced means, but load should be maintained fixed, load power maintained should be fixed, irradiation reduced, the additional power coming from whom? Additional power is coming from battery. Okay, so battery current initially it is negative for the charging condition, for then it is discharging, so current is coming positive. SOC level it is initially charging, then it is discharging. Battery voltage also happen the same thing. First it is battery voltage is high, then suddenly it is reduced some of the value and it is maintaining fixed voltage. So this is some circuit of the Sepik bidirectional converter. We are using Arduino UNO control, but it is not for the closed loop control. We are trying to do it by closed loop, but it is up to for the open loop control. Okay, so we are having some circuit. Okay, so that is we are showing here just for pictorially we are showing here. Okay. Then the most important thing is that hybrid microgrids. Okay, the concept of the hybrid microgrid that we are talking about very initial slides. So what is the importance of the hybrid microgrids? Okay, so in case of hybrid microgrids, whatever structure we have, solar, photovoltaic, and some wind. Okay, so we are using that. This is your DC grid. Another one is the AC grid. But these studies happen for that. Um, Two studies also be there, but here we have presented the work for the standalone condition, means there is no connections of your utility grid. Okay, that also be there, grid connected mode. We are also working on it, but this is not showing here. Okay, so you know that concept of the hybrid microgrid that I have already discussed, so I am not going to repeat them. Main thing is that we have to see the structure of that bidirectional converter, and that it's related to the power management. Okay, power management concept. So power management concept means we are that whatever we are telling, so maintaining the fixed power, okay, maintaining the output voltage, fixed output voltage, and how it will be happen. So that all the part of the power management system, that portion I have already discussed. Okay, some of the simulation result I have shown previously. Now the same kind of thing, some of the simulation result again we can show for the hybrid microgrid system maintaining the power management. Okay, with the variations of the renewables. So how the variations, how the intermittency of the renewables, how the battery power is managed. That's the basic motivations for the power management concepts. Okay, so here you can see it's the structure of the bidirectional converter, and it's an interlinking converter. So system configures a hybrid microgrid. So here you can see first the PV. Photovoltaic is the solar photovoltaic, and wind speed also, wind generator also be there. That is by default. We are not changing anything with the machineries of the wind, nothing. And this is all the by default. Our work is only focused on that, how we are getting the better power management. Okay, we are having some conventional algorithms. Now we are changing that, changing that algorithms to control the bidirectional converters. Okay, that bidirectional converter is there, so controlling them, and with the variations of the load and different conditions, your renewables, how the battery power is managed through this controller. Okay, and that controller can be responsible for that management algorithm, responsible for generating the gate pulses for both the converters. The specifications are given here for the results. Okay, so here that portion I have already told, modeling of bidirectional receiver, that I have already told couple of slides back, how would I design it. Okay, so this is at a discharge condition, charge conditions. Okay, equations are there, same thing. Okay, now power managements in the hybrid microgrids for different conditions. First, we are considering case one. What is the case one? System perform under the variable load power demand with the constant generation. So initially we are considering only photovoltaic, solar photovoltaic. Now we are considering any additional thing, that is our wind. Okay, so what we are doing, so you can see that variable load demand. So load demand, you can see red color, that one, it is varying. The P load is changing with the time. Okay, P load is changing, but you know that other load power is constant generation. So it is your solar photovoltaic power, and it is wind. Okay, so both are constant. Some of the both are constant. Now to who will continue, who will taking the better rest of the thing, who will taking care about those things. So you can see it is battery, you can see it is battery is there. So P battery, so battery is changing. Okay, battery is providing the additional power. So here you can see it is P load and P battery. Okay, so who will taking care about those things, additional load part, that is taking care of the battery. And you know that the changing of the load, so voltage is maintaining fixed. Okay, so here you can see the changing of the SOC level of the battery, so based on the charging mode, then discharging mode. So all those things, it is our SOC level. Then P battery, same thing, this one and this one is same. It is your V battery, voltage of the battery, and current. So current is initially charging, then discharging. That's why P power initially negative. Okay, so P battery initially negative, then 0, then it is coming like that. Okay, so it is your battery voltage. Okay, changing of that value. you can, I think you are able to understand case 1, variations of the load power demand with the constant generations. Okay, now we will do the same thing for under variable solar irradiations and the constant load power. Okay, case 2, variable of solar irradiation. So here you can see the variations of the solar irradiance. So one thing is there, so that irradiance we have changed, it is not the real data. Okay, so if we are taking the real data, then the same pattern, this kind of pattern will not be there. So real data, it having some parabolic type of nature, you can understand. Okay, so it will be look like different, but for the testing purpose, we are doing it for some conditions and checking our the algorithm, is it working fine or not. So solar irradiation, so irradiation is changing. Okay, if it is irradiation is changing, so PVV also being changed. Okay, so PVV is some, it is 10,000. Okay, it is 15,000. Okay, so that's why auto overlapping, so it is not coming properly. So it is coming that P load is fixed. Okay, so it is PPV is changing. Okay, so constant load power, and you know that P battery, how it is changing, so additional P wind also be fixed. Okay, and PPV change with the changing of the PPV, so battery power also being changes. Okay, and that maintaining the load fixed. Okay, based on that value, so we are changing, we can see the SOC level. Okay, P battery power, how is it there? So battery voltage, battery current, okay, charging, then discharging, all the portion you can see battery is charging. Okay, so discharging portion is not there. Okay, as the generation is more than the load demands. Okay, and again third case, what we can see for the under variable solar temperatures. Okay, under variable solar temperature and constant load power. So load power is considering the constant. Okay, so now changing the solar temperature, same thing, that solar temperature is changing over there here. Okay, so like irradiation is making fixed. Now the how it will be look like that, the pattern we can see that battery voltage pattern, battery power pattern, SOC level, and the battery current pattern. Again it will be charging mode. Okay, so discharging mode will be there, so it will be negative side. Okay, as simple as it. So we are maintaining the power management. Okay, hybrid microgrids, and finally that variable under variable wind speed and constant load power. So load power is fixed. Now PV also being fixed. Now wind is suddenly wind power reduce. So reduce means battery also there. That time battery is taking care about that thing. Okay, and maintaining that power. You can see wind variation. So this is not also real time data. We can also use the real time data, so we'll get the patterns. Okay, this is for the only for testing purpose. Okay, testing data. Okay. So here what we will do for under variable wind speed, variable solar irradiation, solar temperature, and the constant load power. Okay, so everything will be varying. Okay, so solar irradiations, temperature, wind speed. So all the things are vary and load power is constant. So who will taking care about rest of the thing will be taking care about the P battery. This is your battery power. Battery power will be maintaining, and we can also get the SOC level, that also can be varied. This is not given here, but it is also varied. And DC voltage almost constant. Some fluctuations are there due to what? Due to changes. Okay. Now variable load power. Okay. Till now we are considering for constant load power. Now all the things are varying. Variable wind speed, variable solar radiation, variable temperature, and load power also varying. So here we can see the natures. Okay, so load voltage is DC voltage is fixed. So we can say like that the power management is making beautifully. Okay, I hope till now all of us can understand. All of you can understand what is the motivations of this work and how the power management is maintaining. Now we are having couple of slides regarding the uh, couple of slides regarding that regarding the microgrids control. Okay, so what are the basic controls idea? So we are talking about different types of control. Okay, here basically we are using the decentralized control. Okay, What do you mean by the decentralized control? System having individuals. Okay, system having individuals controller. Suppose for wind we are focusing about one converters. That converter is controlling by the some of the system. Then solar photovoltaic, some converters are there that also controlled by the MPPT controllers. Okay, then bidirectional converters are there that can be also controlled by some dual loop controls or voltage loop controls. Okay, for maintaining the power management. So what we can see for individual segments, so that is called distributed generation. DG means distributed generations for solar, wind. Okay, any of the other sources will be there, that one. So individually we are using the local controller. Okay, so all the cases local controllers are there. So it is decentralized control. So there is no coordinations between two of the controllers. Okay. So then what we can go for the centralized controller. In case of centralized controller, this is that microgrid central controller. Okay, microgrid central control that having control the different local controllers. Okay, that local controllers are controlling the DG. Okay. What is the problem of the decentralized controller? That making the system more complicated. Okay, if you go for the centralized controller, so only one controller they can control all those things. It is difficult to. This is not difficult to control. It is more complicated system. That's why what we are doing, we are going for the distributed control. In case of distributed control, there is a coordination between the local controllers, all the local controllers, and that local controllers are controlling the DGs. Okay. So that's the distributed control. So this happened. Okay, these are the basic concept of the microgrid control. Means primary control, secondary control, also tertiary control. So now a lot of persons are working on the robust control also. Okay, this all the controlling methods are very common. Okay, so so then we're also working some of the other controls like group control. Yesterday one tutorial session was there based on the group control, then virtual VS, okay, virtual synchronous machine control, then oscillatory controls different. Okay, that also related to the controlling of the microgrids. Okay, so different concepts are there. Okay, we are trying to implement over there. And now another controls a lot of getting very familiar, that is coordination control. So that is called cognitive basic control. Means there are different DGs are there. Okay, so there are coordinations. Okay, coordinations among the DGs. Okay, and coordinating all the sectors. Okay, and it will be controlled through that manner. So I hope you are able to understand. Okay, so what I am telling to you. Okay, and it's an informative session. I hope some of the point you understand, and if you get more clarifications, you can also communicate with me. Okay, so I can also clarify if you are having any more queries. Okay, so thank you all of you. So if you having any query, please let me know so I can. Thank you. Please, if you have any query, please let me know. Ask. Dear participants, any queries? Yes.
Participants can ask questions.
Sir, good morning, sir.
Sir, someone has raised hand.
Please actually.
Please interact with the professor if you have any queries. You can unmute yourself and you can interact, please.
Yes, sir. Yes, sir. Sir, good morning, sir.
Good morning.
Sir, myself Jayanti, sir. Sir, I have one doubt. You said e-vehicle will act as a bidirectional energy storage. How it will act, sir?
E-vehicle is not directly act. E-vehicle having some storage. Okay, so we can connect it that e-vehicle storage through the bidirectional charging station. That what is the motivations of that bidirectional charging station? So vehicle can be charged through that converter. Also, vehicle battery can be charged through that converter. Also, when it is required that vehicle storage. Okay, when a vehicle battery can be discharged on the same converter. So that's why it is called bidirectional charger. Okay.
Okay, sir.
That's
Sir,
yes.
what type of motor will be useful for e-vehicle, sir? E-vehicle application, BLDC motor.
Now, actually, I'm not using money. I'm not designing on that. I'm not working in that vehicle motor. But as per my idea, that lot of work in our department, some of them are working on it. They're using BLDC motor. Okay, that as you have told, then PMS, another synchronous motor they are also using. Okay, PSM. That is Tesla have also has also launched some of the motors. Okay, so lot of work also going on what type of machines using for that vehicles.
Is there any guidance will be having for choosing the motor, sir?
Actually, frankly speaking, I'm not expert on this field. Okay, so I do not have such type of more idea what type of but common idea that I'm talking about BLDC thing. I think those are working in this domain. If you communicate with them, so I hope you'll getting better answer than me actually.
Okay, sir. Thank you so much, sir. Nice
Thank you,
suggestion.
ma'am.
Thank you.
Yes.
Good morning, sir.
Good morning. Yes.
Myself Shashank.
Yes.
Uh, so permanent magnet DC motors also are also used for EVs.
Yes.
Is that reliable, sir?
That I am talking about the same thing that actually I am not working in this machines related thing. Okay, so if you ask me in converter means related that interfacing, so I can give you answer better answer on that way. Okay, so actually this is not for my area of work. Okay, vehicle motors. Okay, we are also planning to incorporate one session. Okay, regarding only vehicle, especially for the vehicle motors application, but that expert is not available, so that's why we are not able to accommodate that person. We're also talking with them. This is also very important area of work. Okay, so that's why we're also planning to accommodate that one, but we are not able to do it. Basically you can understand that all are having a lot of busy schedule. That's it.
Okay, sir. Thank you.
Hello.
Thank you. Please.
Good morning, sir.
Good morning. Yes.
My name is Hardik, sir.
Yes.
Sir, I would like to ask you about the, as far as microgrids are concerned, how are we looking for cyber security challenges?
Cyber security issues means again it goes to the concepts. Okay, so we are using if we say that IoT based control and that that there is a lot of it is called protocols. Okay, so when we are using that IoT based control or any other cyber physical system associated with the microgrids, okay, we are using some of the protocols. So for that issue, we have to using such type of protocols. What happened recently in Ukraine, that Russia and Ukraine were, so a lot of cyber attack was happened, and in that Ukraine, so that hackers are already there. Okay, they are trying to attack to the system server to directly shut down or collapse to the system. That issue recently happened in Ukraine. Okay, at the time of war. So when you are working with the smart grid, that issue already there. So we have to using some protocols, so other unwanted person cannot enter to the system. Okay, but when it will be app based control, when it is open to all, so normally you can do one thing, basic thing what we are doing. There are different type of server. One is global server, one is local server. Okay, so if you restricted the system for the local server, okay, and for accessing the local server from the global server, one window is required, one protocol is required, one verification is required. So we can I hope, I am not a very good in that hacking technology. Definitely there a lot of person are there, those are expert in the ethical hacking. Okay, I think that can be overcome. Okay, so we have to make preserve it is for the local server. That's happened for that IoT based control. Okay, so we are using the system, DCS control, everything will be happen in the local server. Okay. So
Okay.
global server to local server, if we changing, I think some of the cases it can be handled, but still hackers are hackers. Okay, so they are not waiting for whatever server they're using. So good firewall is required for it. I think so.
Okay. Thank you, sir.
Thank you. Yes. Any more queries?
Yes, sir. Good morning, sir.
Good morning.
Sir, I would like to ask, can you suggest some of the research areas where I can get a link, like how we can use different kind of converters in electric vehicles? Like as you said, sir, like we can use renewable energy sources, and there is a scenario between the earlier versions of converters and now what we are using. So in
Basically,
electric vehicles, yeah.
basically,
Yes.
I'm just giving answer for two directions of your question answer. So first, if you are working in microgrids, okay, so microgrid having vast area of work, okay, so it is an interconnected system, okay, so microgrid is associated with different types of converters, okay, so there is a very good work if you pick some idea on the control topologies that we are talking about. Some last few couple of the slides we are talking about different controlling strategies, so that can be a good options of the work if you want to do the different control topologies of the microgrids, okay, for different several converters, okay, there are different controlling method also. Suppose that we are talking about IoT, but this is very vague idea, means if we are working in expert in this basic preliminary level, then we can go for that one for complicated applications. But though if you those are just starting with their work, okay, I can suggest that microgrid control is a good scope of work that is from the microgrid. And in for EV in case of it is some specific domain, okay, so some converter applications in EV, that's good, but the in case of EV, basic idea and a basic research area, maybe the machines aspect, that is number one. That's why I'm getting some of the questions from that end. That is one good options. Another thing is that in management, okay, in BMS, battery management system of the
Yes.
electric vehicle, that also very good idea. Okay, these two are the very grooming idea, very easygoing idea. It automatically it comes to the picture, okay, so in EVs concern, basically persons are more related to about the charging stations, okay. Second thing is that machines aspects, okay, that is very important aspects. And third point is that BMS, okay, and converter is automatically coming to that one, coming to the pictures, okay. Storage means is related to the BMS, that's it. That
Okay,
three
sir.
aspects
Okay.
as per my idea.
Okay. Thank you, sir.
Thank you. Any others query? Any queries from esteemed participants? Okay, I hope there is no other query. Okay,
Thank you
so
so much, sir, for
uh,
such an informative session. Hope our participants get benefited from this session. So now we'll take a 5 minutes break. After that, we'll meet for the next session.
okay, please, I'm requesting all the esteemed participants, please do not leave